In this video, we're going to take a look at finding zeros of polynomials. So a zero of a polynomial or a zero of a polynomial function, f of x, is a number such that when you plug that number into the function, you get out a zero. So a zero of a polynomial function is something that you plug in to the function and the output becomes zero. Zeros are also called roots of the polynomials. So the root of a polynomial is a zero of a polynomial function. Another connection we have with zeros is the connection between zeros and x-intercepts. A zero is some number that when you plug it in, you get out zero. If that number happens to be a real number, then the point r comma 0 is on the graph, and therefore r comma 0 is an x-intercept of the polynomial function. So when our zeros are real numbers, then they yield x-intercepts. Notice that this implies that some zeros may not be real numbers, and therefore they may be complex or imaginary. Let's look at this example to start out with. This question asks us to find the real zeros by looking at the graph of this polynomial function. When I look at this graph, I can see that it crosses the x-axis at 3 points. So I have 3 x-intercepts, one at the x value of -3, another at the x value of 1, and another at the x value of 2. So it looks like I have 3 x-intercepts, and therefore there's 3 real zeros of this polynomial function. X equals -3, x equals 1, and x equals 2. So there we go. That's what we have written down. Again, x-intercepts at -3, 0, 1, 0, and 2, 0. And so the zeros of this polynomial, or the roots of this polynomial, are when x is equal to -3, when x is equal to 1, and when x is equal to 2. Now, those are the real zeros, or the real roots. There also may be some complex zeros or complex roots for this polynomial function that we don't see by just looking at the graph. Now, here's a really important result that we're going to look at and use over and over in this section. The number of linear factors on a polynomial of degree n is going to be n. So every polynomial of degree n, we want n to be bigger than 0. We want n to be an integer bigger than 0. Every polynomial of degree n can be factored as a product of n linear factors over the complex numbers. So if I include complex numbers as my roots, then I can write every polynomial function as a product of a bunch of x minus roots, x minus root, so on and so forth, a lot of x minus roots. Some of these may be repeated. R sub n may be the same number as r sub n minus 1. R sub 2 could be the same thing as r sub 1. But we can factor every polynomial of degree n as a product of n linear factors and then multiplied times maybe some coefficient a sub n. Now, like I said, some of the linear factors could be repeated. You might have x minus 2 and then another copy of x minus 2 and yet another copy of x minus 2, but that's all right. We count that as the multiplicity of whatever root we have. So the number of linear factors that have a 0 of r is the multiplicity of r. By what I mean by having a 0 of r is if we plug in r, do we get out a 0? In this factorization, notice if I plugged in r sub 2 into this term, I would get a 0, and then 0 times anything is 0. So r2 is going to be a 0. R sub 1 is going to be a 0. R sub n is going to be a 0. So the number of linear factors that have 0 of r is the multiplicity of r. Let's look at a couple of examples. Here we have f of x and g of x. And we're going to find the zeros and their multiplicities for each of the two functions, f of x and g of x. It's going to be a fairly straightforward process because f of x and g of x are already factored into a bunch of linear pieces. Let's go ahead and do that. All right, so here we go. We're going to find zeros and multiplicities. Notice that if I plug in a 3 into x minus 3, I get a 0. So one of the zeros is the number 3. Okay. By the way, this 2, this coefficient, doesn't ever become 0, so I can kind of ignore that when finding the zeros. Also, when I plug in 6, I get a 0. So 6 is also a 0. When I plug in a negative 2, I get a 0. And when I plug in a positive 11, I get a 0. In this case, there's no other values that I can plug in to get a 0. In other words, we're saying my output needs to be 0. What equations work? And so I'm setting x minus 3 equal to 0, x minus 6 equal to 0, x plus 2 equal to 0, and x minus 11 equal to 0. That gives me 4 different zeros. And let's look at the multiplicities. The multiplicities are pretty obvious because that goes with the exponents. Here, we have x minus 3 squared. Again, that's like x minus 3 times x minus 3. I'm not going to rewrite that out. That means it has multiplicity of 2. I can say multiplicity. So the x value of 3 has multiplicity of 2. The x value of 6 has multiplicity of 4 because the factor x minus 6 happens 4 times. The 0 of x equals negative 2 happens 1 time in the factorization, so it has multiplicity of 1. And the factor of x minus 11 happens 1 time in the factorization, So that has multiplicity of 1. If you actually multiplied this polynomial out, you would see that you would get degree 2 times degree 4 times degree 1 times degree 1. So that would give you a degree 8 polynomial function. And when you add up the multiplicities, you'll notice that you get a multiplicity, the multiplicities add up to 8. So this is degree 8. We had 8 linear factors. And when you add up the multiplicities, we get 8. Let's do the same thing for g of x. The first 0 that I see is a 0 of x value of -4. The second one I see is having an x value of a +1. Now be careful on this one. We have x plus 2 minus 4i. When I think of x minus r, that's a 0 of -2 plus 4i, because the minus has to distribute. So it's like, I'm not writing -2 plus 4i in parentheses. So it's x minus this root, 2 plus, oh, excuse me, that was plus a -2. Excuse me, plus 2. So minus 2 gives me a +2. So -2 plus 4i. In the same way over here, we would get a -2 minus 4i if I wrote x minus r. And then the last root is a 7. The multiplicity of the 0 of -4, right, multiplicity, is 1 because that happened only one time. The multiplicity of the x value 1 is 5. So the multiplicity of the 0 of x equals 1 is 5. The multiplicity of -2 plus 4i is 1. The multiplicity of -2 minus 4i is 1. And the multiplicity of 7 is 3. If you multiplied this out, you would get a degree 15 polynomial as your g of x. And you can see that the multiplicities add up to 15. You can also see that these two complex number zeros actually occurred in conjugate pairs. And that's a really interesting thing. You don't always have to have that, but you do have to have that in certain circumstances. So that's zeros and multiplicities. Notice that we didn't fill out the entire table on this one. Sometimes that happens. You'll be given more slots to fill out than you actually have zeros for. Other times it'll match perfectly, where the number of slots you have matches perfectly with the number of zeros that exist. So let's talk about conjugate pairs and complex zeros. It turns out if we have a polynomial of degree n with real coefficients, then the complex zeros are going to have to occur in conjugate pairs. The reason that they have to occur in conjugate pairs is that when you multiply things out if the complex numbers don't occur in conjugate pairs, then we're going to get some complex and imaginary coefficients. Well, if I know my polynomial starts out with real number coefficients, then the complex roots or the complex zeros have to occur in conjugate pairs. So if we have real number coefficients, then the complex roots or complex zeros occur in conjugate pairs. Because of this, it turns out that every polynomial of degree n with real coefficients can be factored into linear pieces and quadratic pieces over the real numbers. So if I have a polynomial of degree n, I can factor it into a bunch of linear pieces where these R1s through RMs are just real numbers, and then a bunch of quadratic pieces where the coefficient of x and the constant number are real numbers. Because anytime I have two complex roots that occur in conjugate pairs, then when I take x minus that complex root times x minus the conjugate pair, you'll get a quadratic in the real numbers. Hopefully that makes sense. Let me do an example real quick to show you what I mean by that. So like in the g of x we had earlier, we had two zeros that were complex numbers which occurred in conjugate pairs. And if we set x minus the first complex root multiplied times x minus the second complex root, so x minus the first value, x minus its conjugate pair, then when you do the multiplication, these complex parts of the plus 4i and the minus 4i will cancel each other. And you'll just get a real coefficient on the x. And then the complex number times its conjugate pair will give us a real number. So x minus a complex number times x minus the conjugate of that first complex number gives me a quadratic with real number coefficients. So if we're factoring over the real numbers, we can get a bunch of linear pieces with real numbers multiplied times each other times as many quadratics as we want. And in particular, that last example with the g of x that we had, we could have done that. So the g of x I had was a bunch of real number roots, bunch of linear pieces, and then I had these two complex pieces which occurred in conjugate pairs. I could have rewritten that as x squared plus 4x plus 20. And so now I have a bunch of, I can write g of x as x minus real roots, bunch of those, and then a quadratic. Now you can't do that with every single polynomial, but the polynomials which have real number coefficients, you can always do it that way. You can always factor this way if we know our polynomial has real number coefficients. So now we're ready to start finding the zeros of polynomial functions with some given information. Let's take the polynomial function p of x. And let's say we know that x minus 3 is a factor of p of x. That also means that when you plug in a 3 into the polynomial, you get out a 0. You can check that that's true if you want. So we know this is a polynomial of degree 3, so we can factor it over the complex numbers into 3 different pieces. So how do we do that given that we know x minus 3 is a factor? Well, we're going to start out by dividing this cubic by x minus 3. Since I know x minus 3 is a factor, I'm going to try to break down this cubic polynomial into x minus 3 times the quadratic piece. And therefore, what I'm going to do is I'm going to divide the cubic polynomial by x minus 3 to see what that quadratic piece will be. So I'm going to do this utilizing synthetic division. I'm going to write a 3 in my box, and then I write the coefficients of x to the third, the coefficient of x squared, the coefficient of x, and the coefficient of my constant, which is my constant, right there. Again, if you forget synthetic division, you can watch a video on that, but 1 drops down, becomes 1. I multiply that by a 3 and I put it underneath the negative 5. So 1 times 3 is 3. Negative 5 plus 3 is a negative 2. Negative 2 times a 3 is a negative 6. Then I add negative 18 minus 6. That gives me a negative 24. Negative 24 times 3 is a negative 72. And that gives me a remainder of 0. Now I know that when you divide that cubic by x minus 3, you get 1x squared minus 2x minus 24. So that means this original polynomial, the original polynomial function that I had, can be rewritten as x minus 3 multiplied times x squared minus 2x minus 24. Now I want to find the zeros of this polynomial function. So I need to find the things that will make x minus 3 0 and the things that will make x squared minus 2x minus 24 equal to 0. In other words, I want to find when this is 0. I know how to solve x minus 3 equal to 0. And I also know how to solve a quadratic being set equal to 0. There's multiple ways of doing that. In this case, this quadratic can be factored over integers. So what I'm going to end up doing is I'm going to set 0 equal to x minus 3 multiplied times x squared minus 2x minus 24. And I'll just factor that quadratic at the end. That quadratic factors into x minus 6 multiplied times x plus 4. Negative factors of negative 24 that add to negative 2 are negative 6 and 4. So that quadratic will factor into x minus 6 times x plus 4. Now I can see my polynomial function's output is factored into 3 linear pieces. So the zeros are the following. The first 0 is x equals 3. I knew that from the start. The second 0 is x equals 6. And the third 0 is x equals negative 4. Those are the zeros or the roots of this polynomial function. All of them happen to be real number zeros, so all of these will correspond to x-intercepts. So that's how we can use factoring and division to help us find zeros of a polynomial. Again, in this case, we were given that x minus 3 is a factor, so we knew x of 3 was going to be a 0. What if we're actually given x equals negative 5 as a 0, and we have this polynomial function? Try to use factoring and division to find the zeros of this polynomial function with this given information. Try this on your own if you want. In a couple of seconds, I will pause, or I will do this. So if you want to try this on your own, you can pause the video. Okay, so I'll do this. Here we have this cubic polynomial function, and we know x equals negative 5 is a 0. That means x plus 5 is going to be a factor of f of x. So I know that x plus 5 will nicely divide x to the third minus x squared minus 37x minus 35. I know that when I say nicely divide, what we mean is we'll have remainder 0. I'll use synthetic division to do my dividing. That goes a little bit quicker. So I put the negative 5 in this upper left-hand box, and then I put the coefficients of my cubic polynomial in the top line. That's going to be 1, negative 1, negative 37, and then negative 35. Now we're ready to go ahead and do the synthetic division. 1 drops straight down. Then I multiply by a negative 5. Negative 5 times 1 is negative 5. Add up negative 1 and negative 5 to give you a negative 6. Negative 6 times negative 5 is a positive 30. What we end up with is a negative 7 when we add 30 and negative 37. Negative 5 times negative 7 is a positive 35. And you get, of course, remainder of 0. And this means that this division comes out to be x squared minus 6x minus 7. And therefore, my polynomial function can be rewritten as x plus 5 multiplied times that quadratic, specifically x squared minus 6x minus 7. We're looking for the zeros of this function, so we want to factor it completely. And once again, in this case, that quadratic on the right can be factored. Factors of negative 7 that add up to a negative 6 are negative 7 and positive 1. So I get a factorization of my polynomial function that says x plus 5 times x minus 7 times x plus 1. That is f of x factored out. If I want to find the zeros of that, I just set the output equal to 0, and then each individual linear piece I set equal to 0. So I have 3 zeros, one of which is x is equal to negative 5. That's the one we were given originally. The other is x equals 7, and the other is x equals negative 1. So once again, cubic polynomial we ended up with 3 zeros, each with multiplicity of 1. So that's how we can utilize division and factoring to end up with finding zeros of a polynomial function. Let's do another example. Again, if you'd like to try this on your own, push pause on the video. I will do this one in a couple of seconds. All right, so let's take a look at this one. Again, we're given that x minus 2 is a factor, so we already know that, which means that x of 0 is going to be a 0. So not x of 0, x of 2 is going to be a 0. So x equals 2 is going to be a 0. We know x minus 2 is going to be a factor. So again, I'll utilize synthetic division, write out in the box over here on the left 2, and then on my first line, I write out the coefficients of my polynomial. That is 1, -4, 9, and -10. Drop the 1 down, multiply by 2, add, you get a -2, multiply by 2 again, you'll get a -4. Add those two and you get a 5. Multiply that by a 2 and you get a 10. And just like we expected, we got a remainder of 0. So that means when you divide these two things, you get the quadratic x squared minus 2x plus 5 with remainder 0. We knew it was going to be remainder 0 because we knew that x minus 2 is a factor. So if I have this, that dividing by x minus 2 gives me this quadratic, then if I multiply both sides by x minus 2, I see that my g of x can be rewritten as x minus 2 times x squared minus 2x plus 5. Now, in this case, we start looking at factors of 5. There are no factors of 5 which are going to add up to give me -2. No integer factors of 5 that add up to give me -2. So what I have to do in this case is essentially set my first piece equal to 0 and then set the quadratic equal to 0. When I set the first piece equal to 0, then it's obvious that I have a 0 when x is equal to 2. I already knew that. When I set my second piece equal to 0, in order to solve that, I would utilize a quadratic formula. Factoring doesn't work, so I'll jump right to the quadratic formula. Hopefully we all remember that the quadratic formula is opposite of b plus or minus the square root of b squared minus 4ac all over 2a, which if we're utilizing this quadratic, a is 1, b is -2, and c is 5. So opposite of b would be the opposite of -2, that's +2, plus or minus the square root of b squared, that is -2 squared. I'll just write it that way. Minus 4 times 1 times c, that's 5. All over 2 times a. 2 times 1 is 2. I get -2 squared, that's going to be a 4, minus 20. That ends up as a -16 underneath that square root. So that is equal to fraction 2 plus or minus. We're going to get 4i divided by 2, which is two solutions. One is 1 plus 2i, and the other is 1 minus 2i. And those are my other two zeros. So I got 1 0 from the linear factor, and that was a real zero. And I got two complex zeros from this quadratic piece. And one of those zeros is 1 plus 2i. The other zero is 1 minus 2i. So there you go. That's the idea. So this shows how to find the zeros using division and then utilizing this factoring. We know how to solve linear equations. We know how to solve quadratic equations. So if we can break things down into linear pieces and quadratic pieces, then we can solve each of those when we set each of those pieces equal to 0. And obviously, in our quadratic, sometimes we get complex numbers. So this cubic polynomial function had 3 zeros, 2 of which are complex numbers. The real number would be associated with an x-intercept. So this function, when you graph it, would have one x-intercept but it has 3 zeros, 2 of which are complex. Let's do one more example that's similar. We're given a piece of information. The piece of information we're given is that x is equal to -1 is a 0. You can check that out by plugging in -1 into the function itself. -1 to the third plus 12 times -1 plus 13. That'll give you a 0. And then trying to figure this out. So we have that piece of information, and we want to find the other zeros of this function. Go ahead and push pause on the video if you want to try this on your own. Otherwise, I'll do it in a couple of seconds. All right, so given that x is -1 is a 0, we know that x plus 1 is a factor. We're going to take our cubic polynomial output and divide it by x plus 1. So I put a -1 in the box, and then I put coefficients of that cubic polynomial in the first line. Now be careful, we don't have an x squared term. We have to have a placeholder for that. So we put 0 as the placeholder for the x squared term. Other than that, it's pretty straightforward. So the 1 drops down. We multiply that by a -1. 1 times -1 is -1. Add those two up, you get a -1. -1 times -1 is a positive 1. Add those two up and you get a positive 13. Positive 13 times -1 is -13. Add those up, you get remainder of 0. So that division comes out as x squared minus 1x plus 13, which means my function, my f of x, can be written as the polynomial x plus 1 multiplied times x squared minus x plus 13. And then I do the same thing that I did in the previous case. I would set 0 equal to both x plus 1 and 0 is equal to x squared minus x plus 13. I'm doing that because x squared minus x plus 13 does not factor over the integers. So I look at factors of 13, none of those pairs add to -1, and so I'll just set 0 equal to that quadratic. And then obviously we're going to take x equals -1 as our first 0. Let me just write that down. That's the one I was given. And then to find the other two zeros, I plug in the quadratic formula. So x is equal to opposite of b plus or minus square root of b squared minus 4ac AC all over 2a. In this case, b is -1, so opposite of -1 is a +1. When I take -1 and square it, I'll get +1. In this case, a is 1, so 1 times anything is itself. And c is obviously 13. Inside that square root, I'm getting a -51. So this turns out as the fraction whose numerator is 1 is 1 plus or minus the square root of -51, all over 2. This is obviously a complex number. By the way, if this were a +51, then it would not be a complex number, but it would be an irrational number. But we have a -51, so I can factor out that negative as an I. This gives me two more zeros, I should say. The first is, let me rewrite this, excuse me. If I think about it, I'll write it this way. 1/2 plus the square root of 51 divided by 2 times I. And the other is going to be the complex conjugate of that, which is 1/2 minus the square root of 51 divided by 2 times I. Again, you can see that since our function started with real number coefficients, our complex roots occurred in conjugate pairs. So there we go. That's how we can find zeros of these polynomial functions if I'm given some piece of information. So the obvious question goes like this. What if we are not given any starting information? What if we don't know a given root or a given zero? Or what if we don't have any initial information? Where can we go about trying to find zeros as opposed to just trying to plug in every number we can think of and checking? Well, there's something called a rational zeros theorem for polynomials with rational coefficients. So if a polynomial has rational coefficients, then any rational zeros will have the form b over c, where b is a factor of my constant term, and c is a factor of the leading coefficient. This gives me an organized way to check for rational zeros of our polynomial. Now, this doesn't give me irrational zeros of our polynomial. It doesn't give me the complex zeros, but it will give me all the rational zeros of the polynomial. So the rational zeros theorem is just that. It gives me a way to pare down my choices for the zeros, which will be rational numbers. Let's do an example to show how this works. We have f of x is equal to x to the third minus x squared minus 10x minus 10. This cubic polynomial has all rational number coefficients. Therefore, I can use the rational zeros theorem, and along with the other tools that we've been using, to find the zeros of this polynomial function. So the rational zeros theorem says all rational zeros will be of the form b over c, where b is a factor of the constant term and c is a factor of the leading term. So options for b are going to be, well, there's going to be a lot of them. What are factors of -8? Well, we can take -8 by itself. We can also take +8. Another factor of -8 is -4. Another factor is a +4. And then -2 is a factor. +2 is a factor. -1 is a factor. And +1 is a factor. My options for C are more limited. Factors of 1 are -1 and 1. That means my options for rational zeros are the following. Again, these are all going to be options. So these are going to be options for x. I would take -8 divided by -1 and -8 divided by +1. So I get a +8 and a -8. Then I take 8 divided by -1 and 8 divided by +1. That gives me -8, +8 again, so I won't write those down again. Notice that dividing by a -1, dividing by +1, I can actually just divide everything by a +1 because I've already included the negative and positive options for B. So in this case, 8, -8, 4, -4, 2, -2, 1, and -1 are my options. These are whole numbers. Obviously, if C had more options, we might get some rational numbers there as well. Now all we do is we plug in all of these values. We'll plug in 8, then we'll plug in -8, and then we'll plug in 4, and then we'll plug in -4, and then we'll plug in 2, and we'll see which ones of those give zeros. And this is much more effective than trying to plug in all rational numbers because there's infinitely many rational numbers. Here, there's only finitely many options that could give me 0. So let's go ahead and start by plugging in 8. 8 to the third minus 8 squared minus 10 times 8 minus 8 gives me 360. So obviously 8 is not a rational 0. What would I get when I plugged in a negative 8? Well, I would take negative 8 to the third minus quantity negative 8 squared minus 10 times negative 8 minus 8. That gives me a negative 504. So 8 and negative 8 are not going to be zeros of my polynomial function. Let's try 4, and then we'll try negative 4. Again, all I'm doing is I'm plugging in this number into my function and having my calculator give me the output. So I take 4 cubed minus 4 squared minus 10 times 4 minus 8. Let me put that in parentheses, look a little bit nicer. So I'm plugging in 4. And when I do that, I haven't quite done that yet, but this time I do get a 0. So when I plug in a 4, I get a 0. So that means x equals 4 is a 0 for my rational, or for my polynomial function. That x equals 4 is a rational 0 of my polynomial function. If you wanted to, we could do the things we did earlier right now. Once I have that x equals 4 is a 0, I could state that, well, one factor is going to be an x minus 4, and so I divide and break it down like we've done previously. So just like we did in this case, now I know 4 is a factor, so x minus 4, then divide, then break it down. Hopefully we can factor, and if it doesn't factor, then we could use the quadratic formula to get my other zeros. However, a lot of the time, it's worth just plugging in all of these other numbers to see if we can find other zeros. So let's plug in a negative 4 as well. If I plug in a negative 4, I get a negative 48. What would happen if I were to have plugged in a 2? Well, it turns out if I plug in a 2, I get a 24, excuse me, a negative 24. What would happen if I plugged in a negative 2? Well, if I plugged in a negative 2, I also get a 0. So I know negative 2 is a 0 as well of this function. What would happen if I plugged in a positive 1? Well, just plug that in. You'll get a negative 18. I've plugged a lot of these in before, so I've already checked. What would happen if I plugged in a negative 1? Well, if I plug in a negative 1, I get out a 0. Notice that this gave me all 3 zeros. I knew there was going to be at least 3 counting multiplicities. So the number of zeros was going to be 3 if I count the number of multiplicities. And it turns out I got 3 unique zeros. And therefore, this polynomial function, this f of x, has 3 unique zeros. One of which is x equals 4. The other is x equals -2. And the last one is x equals -1. Those are the 3 zeros. And because of this, I actually know that my function f of x is going to factor as x minus 4 times x plus 2 times x plus 1. It's degree 3. We have 3 linear factors, and the coefficient in front of the x to the third is just a 1. So it'll factor this way. So there you go. That's how we can utilize the rational zeros theorem. And again, it's much better than just trying to plug in a bunch of numerical values that have no order or thought behind them. So you could spend all day plugging in values if I didn't have a nice place to look. So the rational zeros theorems narrows down our options for the rational zeros. We plug those in, see which ones give a 0. In this case, all 3 of my zeros were rational numbers. In other cases, you only might get 1 or 2 zeros being rational numbers. Let's take a look at this one. We'll use the rational zeros theorem and whatever other tools we have to find zeros of this polynomial function. P of x is equal to x to the third plus 2x squared minus 17x plus 6. If you want to try this on your own, push pause on the video. In a couple of seconds, I will show you how it's done. This polynomial has nice integer coefficients, so I can use the rational zeros theorem. Again, integer coefficients, that's when we use the rational zeros theorem. All the rational zeros are going to be of the form b over c, where b is a factor of 6 and c is a factor of 1. So I look at factors of 6. That would be 6 and -6, 3 and -3, 2 and -2, 1 and -1. Factors for C, which again is just options for C. C has to be a factor of this lead coefficient. So basically I get a +1 or a -1. It's always the nicest when C is 1 or -1. If C is multiple things, if I have lots and lots of options for C, then it's harder to do. So anyways, rational zeros, I can take 6 divided by 1, that's a 6. I can take 6 divided by -1, that's a -6. -6 divided by 1 is -6, I already wrote that down. -6 divided by -1 is a +6, I already wrote that down. You'll see that in each case, that's what we get. So we get 6, -6, also 3, -3, also 2, -2, and also 1, -1. So that's what's going on. This was P of x, so I just plug in my values into my function. So when I plug in 6, I would do 6 cubed plus 2 times 6 squared. Excuse me, I hit it wrong thing. Minus 17 times 6 plus 6. When I plugged in 6, I got 192. When I plugged in negative 6, I got negative 36. When I plugged in 3, I got a 0. Again, I could stop there and do operations, but I'll just test all these. When I plugged in a negative 3, I ended up with 48. When I plug in a 2, I end up with negative 12. When I plug in a negative 2, I end up with a positive 40. Let's try 1 and negative 1. When I plug in a 1, I end up with a negative 8. And when I plug in a negative 1, I end up with a positive 24. Oop. By the way, this shows you also between, somewhere between x value of negative 1 and an x value of 1, we go from positive output to negative output. So somewhere between negative 1 and 1, there is a 0. What this is saying, since my only options for rational zeros are these ones, is that the 0 between negative 1 and positive 1 is not rational. In other words, it's irrational. But this does give me one rational 0. That is the value of 3. So we have one rational 0, and that is the value of x equals 3. If I want to find the other rational, not rational, the other zeros, I know that the polynomial has to have a factor of x minus 3. So this polynomial is going to be able to be rewritten as x minus 3 times a quadratic. I say times a quadratic because it's to the third power. And moreover, I don't know if I can do that. No. I get that quadratic by just taking this polynomial and dividing by x minus 3. So we go back to what we were doing before to find my other zeros. So let's go ahead and do that. Now we're at a place where I know one piece of information along with my given cubic polynomial. We can find the other zeros using this. Let me rewrite, space that out a little bit differently. I'll write it like this. So just like we did before, we know we have one rational 0 for this polynomial function. So we have a factor of x minus 3. I'm going to divide that polynomial by x minus 3. I'll use synthetic division like we usually do. So coefficients of my original polynomial on the first line, that is 1, 2, -17, and +6. Synthetic division says drop that 1 down, multiply by 3. That'll give you 3. Add those two, you get 5. Multiply by 3, you get a 15. Add -17 and 15, you get a -2. Multiply that by 3, you get a -6. And we get remainder 0. So after we do the polynomial division, we know the quotient is x squared plus 5x minus 2. So that means this polynomial, this p of x, polynomial function, can be written as x minus 3 times x squared plus 5x minus 2. We already know the 0 when we have x minus 3 set equal to 0. That's the 0 of 3. Then we say what would happen if we set the other piece equal to 0. So we set the quadratic equal to 0. And I'm just going to write this down. Opposite of b will be -5 plus or minus the square root of b squared minus 4 times 1 times -2 all over 2 times 1. So b squared minus 4ac, that's 25 plus 8 inside of the square root. 25 plus 8 is 33. So I can simplify that to -5 plus or minus the square root of 33, all divided by 2. Now I know that all three of my zeros. I have 1 0, which is x equals 3. That's the one I found using the rational zeros theorem. And then I have these two other zeros, one of which is x is equal to opposite of 5 plus the square root of 33 over 2. And the other, which is x is equal to opposite of 5 minus the square root of 33 all over 2. That minus actually is in the wrong spot. I have to have it in the numerator for this to work. So there you go. Those are the 3 zeros of the polynomial function that I was given. All 3 are real number zeros, but there's only one which is a rational number, and that's x equals 3. These two are irrational because square root of 33 is irrational. By the way, you may notice that with these integer coefficients of my polynomial, the irrational zeros also came out in sort of an irrational conjugate pair. This is not a complex conjugate, but they're kind of irrational conjugate pairs. Interestingly enough. So we had a rational 0, and then the two irrational came out in conjugate pairs, and that was because our polynomial function started with rational coefficients, in particular, integer coefficients. Let's try another example. If you want to try this on your own, push pause on the video This is a quadratic polynomial, and we want to find the zeros for this polynomial function. Start by using the rational zeros theorem, and then use any other tools that you want. Again, if you want to try this on your own, push pause on the video. I will do it in a couple of seconds. All right, this one's pretty straightforward as far as the rational zeros because we don't have a lot of options. Rational zeros are always b over c, where b is a factor of our constant, c is a factor of the coefficient of our leading term, so our lead coefficient. Our constant number is -1, so the only options for b are 1 and -1. Our leading coefficient is a 1, so the only options for c are 1 and -1. If I take 1 divided by 1 or 1 divided by -1, -1 divided by 1, -1 divided by -1, I get only two options for rational zeros. One is a positive 1 and the other is a -1. If I plug in a positive 1, it turns out I get a -16. So that is not a rational zero. If I plug in a -1, I do get a 0. So I know that -1 is a 0. And that means my polynomial has a factor of x plus 1. So now I'll make my degree on this polynomial. Well, I'll split up my polynomial by doing division. So we'll take that x to the fourth minus 2x to the third minus 8x squared minus 6x minus 1. And we'll divide it by x plus 1. Again, as we typically do, we'll utilize synthetic division when we do that. So here we go. Plug in -1 into the box, and then my coefficients are going to be 1, -2, -8, -6, and -1. Then we start our synthetic division process, drop 1 down. 1 times -1 is -1. Add -2 plus -1, get a -3. Times -1 is a +3. Add, that'll become -5. Times a -1 is a +5. Add those up, we get a -1. And then -1 times -1 is a +1. Those add to 0. And so the division gets us that this fourth degree polynomial divided by x plus 1 gives me x to the third minus 3x squared minus 5x minus 1. Now I know that the polynomial, the f of x, can be factored as x plus 1 multiplied times that cubic polynomial that I just got through division. Then we ask, well, I know that x plus 1 is 0 when x is -1. When is x to the third minus 3x squared minus 5x minus 1 equal to 0? So in other words, when is this equation true? And we'd say, well, this is a cubic polynomial. There's no nice quadratic function on a cubic polynomial, but what I can do is I can do exactly the same thing I did here on that cubic polynomial, because that has rational coefficients, specifically integer coefficients. So the rational zeros are all going to be of the form. Let me just start a new page. Of 1 or -1. If I plug in, again, this won't be into my function. This will be into sort of this cubic. Let's call this cubic. Instead of f, we'll call it h of x. So that part we'll call h of x. And then we'll say, what happens when I plug in a 1? Well, when I plug in a 1, I end up with a -8. What's going to happen when I plug in a -1? When I plug in a -1 there, I end up with -1 minus 3 plus 5 minus 1, which is 0. That means this cubic can also be divided by x plus 1. So in other words, h of x has a 0 of x equals -1, also has a factor of x plus 1. So I can go ahead and divide that h of x by x plus 1 as well. Let's go ahead and do that. X to the third minus 3x squared minus 5x minus 1. Divide that by x plus 1. Once again, I'll use synthetic division and do it that way. I've already listed out the synthetic division. In the box, we put a -1, and then the coefficients of 1, -3, -5, -1 go in the first row. I drop down that 1, and then multiply times -1, we get a -1. Add, that gives me a -4. -4 times a -1 becomes a +4. Add, that would give me a -1. -1 times -1 is a +1. When I add those two up, I get a 0. That means when I divide x to the third minus x to the minus x squared minus 5x minus 1 by x plus 1, I end up with the quadratic of x squared minus 4x minus 1. Now, think about what my original function was. My original function was x plus 1 times this cubic. This cubic, I know, has another factor of x plus 1. So we're ending up with two factors of x plus 1 for my f of x. Let me just copy this. And I'm saying that this cubic function can be replaced with another factor of x plus 1 times this quadratic of x squared minus 4x minus 1. So that's what we're saying about my original function f of x. And then I could say, can I factor this quadratic? Turns out I can't. There's no factors of -1 that add to -4. But I could solve that quadratic equation when I set it equal to 0. If I do that, x is equal to, well, let me also just throw in we can also solve for x when x plus 1 is equal to 0. And then we'll solve for x when the quadratic is set equal to 0. When the quadratic is set equal to 0, I say opposite of b, that's going to be a +4 plus or minus the square root of b squared, which is 16, minus 4 times a, which is 1, times c, which is -1, all over 2 times a, which is 2 times 1. Notice what happens. B squared minus 4ac is going to give me 16 plus 4, which is a 20. I'll simplify that quickly. The square root of 20, 20 is like 4 times 5. The square root of 4 is 2, so I'm getting 4 plus or minus 2 times the square root of 5 all over 2. When I divide both pieces, I get two irrational numbers, one which is 2 plus the square root of 5, and the other which is 2 minus the square root of 5. So this gives me 3 zeros. One of my zeros, as we saw, had multiplicity of 2 because it wound up in my factorization twice. And the other two were irrational numbers, 2 plus root 5 and 2 minus root 5. So x is equal to -1. That's one of the zeros. The other zero is 2 plus the square root of 5. And then the last zero is 2 minus the square root of 5. This one was kind of a long one because we had this 0 of -1, which had multiplicity of 2, and that caused me to do synthetic division, or dividing by x plus 1, twice in a row, essentially. We had to divide x plus 1 first, then we had to divide by another x plus 1, and then we had to solve a quadratic. So we got 3 zeros, one of which had multiplicity of 2. All right, now what if we have a 4th degree polynomial function, but it doesn't have any rational zeros? All right. Well, here's the deal. If I were to try to solve this, and if I would look at factors of 120, we'd have a lot of factors. We'd have 120, -120, 60, -60, 40, -40, 30, -30, 20, -20. We have lots and lots and lots of options, okay? It turns out if you went through all of those options, this has no rational zeros. So we'd be kind of stuck if we did the rational zeros theorem with this one. But we're lucky in that we know x is equal to 3 minus I is a 0. So how could we take advantage of having this 4th degree polynomial, knowing that 3 minus I is a 0? How could we find the other zeros of this polynomial function? Let's go ahead and do that. Now, the first thing that we notice about this polynomial function is that all of the coefficients are nice integer values. Therefore, if I know one of the zeros is a complex number, I also know another zero that is a complex number, and that's the complex conjugate. 3 plus I is also a zero. Remember, complex zeros occur in conjugate pairs if our polynomial has real number coefficients. So I know 3 plus I is a zero. Also, 3 minus I is zero. So since 3 minus I is a zero, 3 plus I is also a zero. Okay. Now you can do a couple of things. If you wanted to, you could take x minus 3 minus I is a factor. And we could divide with complex numbers, divide 3 minus I. You could do that using synthetic division if you'd like. So we could divide using synthetic division with complex numbers. Usually I don't do that though. Usually what I do is I say, well, also this is a factor. When I multiply x minus the complex number 3 minus I times x minus the complex number 3 plus I, these two should both be factors. And when I multiply these two out, I would get x squared minus 3 plus I times x minus 3 minus I times x, and then plus 3 minus I times 3 plus I. I'm just multiplying polynomials there. That gives me x squared. The coefficient on x is a minus 3 minus I minus 3 plus I. So the I and the minus I are going to cancel each other out. You'll get a negative 3x and a negative 3x. That's minus 6x. Here we'll have 3 times 3, which is 9. And then I'd get minus I squared. The middle terms would cancel out. 9 minus a negative 1 is 9 plus 1, which is 10. So I know this quadratic is a factor of this fourth degree polynomial. Therefore, what I can do is I can take this fourth degree polynomial and divide. Instead of dividing by a linear piece, I'll divide by this quadratic. So I take this fourth degree polynomial and divide it by x squared minus 6x plus 10. This I cannot do using synthetic division easily. So I'd use long division on this one to divide. I'll go ahead and do that for you right now. Again, I've worked that out. So here's the way it looks. We would put the divisor out front and then the dividend inside. We'd ask, what do I need to multiply by x squared to get an x to the fourth? That's an x squared. So x squared times this polynomial becomes x to the fourth minus 6x to the third plus 10x squared. Then I would subtract that. I'd get 4x to the third minus 12x squared minus 32x plus 120. Then I'd ask, what do I need to multiply by x squared to get this 4x to the third? The answer to that is 4x. Then I take 4x times this polynomial. That gives me 4x to the third minus 24x squared plus 40x. If I subtract that polynomial from this one, I end up with 12x squared minus 72x plus 120. And then I say, what do I need to multiply x squared by to get 12x squared? And the answer to that is just a 12. 12 times that polynomial becomes 12x squared minus 72x plus 120. When I subtract that, I get a 0, just like I had hoped. So we get remainder 0. That means when I divide these two polynomials, I end up getting x squared plus 4x plus 12 using long division. Now, remember, my original function was this fourth degree polynomial. And what I'm saying is that fourth degree polynomial can be written as this quadratic times this quadratic. So let's go ahead and do that. So there you go. I have written the polynomial in both ways. Fourth degree polynomial is equal to the first quadratic times the second quadratic. And now we can solve both. Now we don't really need to solve this first equation when we set that first equation equal to 0. I say first equation set equal to 0. I mean the first polynomial equal to 0, because I already know that 3 plus I and 3 minus I are the solution to this one. What we need to do is solve for the second quadratic set equal to 0. So again, the first one gives me x is equal to 3 plus I and x is equal to 3 minus I. That's what we saw earlier. The second one would give me an x value. Well, this one doesn't factor. No, it does factor. Do factors of 12? Yeah, I can actually solve that second one. Excuse me. I didn't even realize that. Nope. Can we factor? No, I'm sorry. We cannot factor. There's no factors of positive 12 that add up to a positive 4. If we had a negative 12, we'd be good to go. But in this case, no factors of positive 12 that add up to a negative 4. So we are going to have to use the quadratic formula, which is opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. In this case, 16 minus 4 times 12 gives me a negative 32. So I end up with negative 4 plus or minus the square root of negative 32 all over 2a. Now the negative there can become an I when I take it out front. 32 is like 2 times 16. Square root of 16 is 4. So I can take 4i times the square root of 2 divided by 2. Those are my two answers. And again, if we want to make that look a little bit nicer, I'll delete that. That's going to be -2 plus or minus 2 times I times the square root of 2. This gives me all 4 zeros. Here we had 3 plus I as a 0. We had 3 minus I as a 0. We had -2 plus, and you can say this in a number of different ways. Some people would say 2 times the square root of 2 times I. Others would say 2I times square root of 2. And then the last one is -2 minus 2 times the square root of 2 times I. Again, that I is not underneath the square root. Let me try to get that all on the same line. There we go. So here are our 4 different zeros, which all happen to be complex numbers. So that's how we can do an example like this. If I'm given a polynomial function, it has no rational zeros. You could have done the rational zeros theorem. I want to save time, so I don't want to do that. And checked all factors of 120. You would have found none of them give you a 0. But since we know 3 minus I is a 0, we know its complex conjugate is also a 0. We can use those two to give me a quadratic that will divide my original polynomial. When I do that, I'll get another quadratic in this case. And then I can solve both quadratics. So quadratic equation number 1 set equal to 0 gives me 3 plus I and 3 minus I. I knew that from the factorization. And then the second quadratic set equal to 0 gives me -2 plus 2 root 2 times I, -2 minus 2 root 2 times I. That's quite a long problem, but it's an interesting problem in how we get it. All right, let's do one more example without a hint. This will be the last one. We're going to use the rational zeros theorem and other tools to find zeros of this polynomial function. Here we can see that we have rational numbers, but lots of them are being divided by 2. So lots of them have a denominator. And that is what f of x is. So f of x is this 4th degree polynomial with these coefficients. These coefficients are rational numbers, so we can use the rational zeros theorem. But I'm going to kind of adjust it when I do this. Let's go ahead and do this problem. If you want to try it on your own, just push pause on the video. Now, what I would do is, first off, I have to realize that I'm really setting 0 equal to this polynomial, and I want to solve this equation here. That's how I find my zeros. So it's perfectly fine if instead of using the actual original f of x, if I multiply both sides by a 2. Or you could think of factoring out a 1/2 for my f of x. If I multiply both sides by a 2 or factor out a 1/2, I'm going to end up with a coefficient of 1 in front of x to the fourth, a coefficient of -5 in front of x to the third, a coefficient of +13 in front of x squared, a coefficient of -19 in front of the x, and a 10 as my constant. So that's just multiplying both sides of this by 2. Again, you can also think of this as taking my original f of x and factoring out a 1/2, factoring out that original coefficient. And what that does in effect is it makes all of my coefficients that I'm worried about now integers. So I'm going to find the zeros of this x to the fourth polynomial so that all of my coefficients are zeros. Then I can use the rational zeros theorem. I'm going to be looking at factors of 10. So 10 and -10, 5 and -5, 2 and -2, 1 and -1. And my options for the C, well, again, I'm looking at this polynomial with integer coefficients. So the C there has to be some factor of 1. So that means either 1 or -1. Again, if you have more options, then this can become a lot of options, but essentially I get 10, -10, 5, -5, 2, -2, 1, and -1 as my options for rational zeros. You can either plug this into my original f of x, or I could plug it into the polynomial where I've multiplied both sides by a 2. Doesn't matter if plugging them into f of x gets me 0, then plugging into this polynomial will also give me 0, and vice versa. So the way I'm going to write it is here. And I'm just going to plug it in to my f of x. So we plug in, let's start with +10. When I plug in a +10 into my polynomial function, I get 6,120 divided by 2, which is 3,060. That's into my original function. If you plugged it into this one, you get double that, which is 6,120. What would happen if I plugged in a -10? Well, I'd get 8,250. What if I plugged in a 5? Let's go ahead and plug in a 5. I get 120. If I plugged in a -5, I believe I get 840. If I plug in a 2, I get a 0. That's great. Now I found a 0. If I plug in a -2, I get 78. If I plug in a 1, I get a 0. That's a good thing. If I plug in a -1 into my original function, I get 24. Again, if you plug them into the original function, I believe you get these numbers. I might have a miscalculation. Hopefully I don't. If you plugged it into this, where we factored out a 1, then you just get double all these numbers. But in either case, the zeros come out where we have two of them. One is x equals 2, one is x equals 1. So we have two zeros, two rational zeros. One is x equals 2, and the other is x equals 1. Okay. Now, this was a fourth degree polynomial. So we should end up with two other zeros, or at least some multiplicity there. Instead of using my original function now, I'm going to use the version where I've factored out the 1/2. And what I'm going to do is I'm going to take that fourth degree polynomial, since I know that this has a 0 of 2, I'm going to take that fourth degree polynomial and divide it by x minus 2. I'll use synthetic division to do that. In fact, I'll do that on my own real quick. So here's that division. We've done that, and dividing by x minus 2 gave me x to the third minus 3x squared plus 7x minus 5. So that's my f of x. My f of x is 1/2 times the quantity x minus 2 times the quantity x to the third minus 3x squared plus 7x minus 5. If you want to, you can push pause and go see that you can do it, but that's not the important part. Now, remember, we also had the 0 of x equals 1. So we can do synthetic division on this polynomial as well, this x to the third, since we know x minus 1 is going to be a factor. Let's go ahead and do that. I'll do that on my own here. And here that work is. So we took the cubic, divided it by x minus 1. I did that using synthetic division right here. And we got out the quadratic of x squared minus 2x plus 5. So now I know that my original function can be written as 1/2 times x minus 2 times x minus 1 times this quadratic. Now, this quadratic can't be factored over the real numbers, or excuse me, over the integers. So there's no factors of 5 that add up to -2, but we can use the quadratic formula to solve this quadratic. So let's go ahead and do that. Let's use the quadratic formula to solve, specifically solving 0 is equal to x squared minus 2x plus 5. We already know that we can get an x value of 2 as a 0 here and an x value of 1 as a 0. So this quadratic will give me the other two zeros. Opposite of b will be 2 plus or minus the square root of b squared, which is 4, minus 4 times a times c, all divided by 2a. This is going to be 4 minus 4 times 5. That's a -16. And we've done this earlier. So square root of a -1 is an I. Square root of 16 is 4. So that's 2 plus or minus 4i, which is 1 plus or minus 2i. So that gives me the two solutions to this quadratic equation, and that means I have 4 zeros overall. The zeros of my polynomial function are x equals 2. That comes from the first linear piece. X equals 1. That comes from the second linear piece. And then x equals 1 plus 2i. X equals 1 minus 2i. Those two come from that quadratic piece. So this is how we can utilize the rational zeros theorem along with some other tools like solving a quadratic equation to find zeros of polynomial functions. Here we also factor out 1/2 or multiplied by 2 to begin with. So this rational zeros theorem, along with these other tools, are really effective at finding zeros for polynomial functions. Obviously, these tools aren't complete. Like if I didn't know that 3 minus I was a zero of this one, I would have been stuck in example 10. So there are some polynomial functions that are really hard to deal with, but most of them I can find a 0 for, a rational 0 for. And I want to state in particular, when we have a cubic or a fifth degree polynomial, we know that based on the end behavior, one side goes to positive infinity and the other side is going to shoot off to negative infinity. By the intermediate value theorem, we have to cross the x-axis somewhere. So with a polynomial of odd degree, we know that type of polynomial function will have at least one real zero. We know that by the end behavior because it has to cross the x-axis. We also know that based on some of the other things we looked at earlier, specifically this thing. If it's an odd degree, then we have to have at least one real zero, along with maybe some complex zeros. I think I like thinking of it as the end behavior better. So I know that this is odd degree. I know it has to cross the x-axis somewhere, so it has to have a real zero. In any case, this shows us a lot of tools we can use to find zeros of polynomial functions. And that's the end of this video.